We have a 10,000-foot runway, and we have Michael on one end of the runway and Aaron on the other end of the runway. And they're running towards each other. Michael's speed is 15 feet per second, Aaron's speed is 8 feet per second. And we are going to use our ideas of a coordinate system in order to find when and where Michael and Aaron meet. In order to specify where they meet, we need to impose a coordinate system. So, we need in particular to specify M's position and A's position with respect to some coordinate system. Let's imagine a y-axis and x-axis drawn in like this. I could have chosen to draw a different coordinate system, but this one seems like a natural choice. Now, I have Michael's initial position as 0, 0, and Aaron's initial position as 10,000, 0. I've written this as m equals 0, 0, but I'm a little hesitant about this, in particular because m is moving. So what I want to say is that m's initial position is 0, 0, and Aaron's initial position is 0, 0. How should I specify that I'm talking about their initial position? Well, I'll write this. And I hope the notation that I've used makes you think of a function. What I'm saying is that m's position at time 0 is 0, 0, and Aaron's position at time 0 is 10,000, 0. What I'd like to do, and what we'll be doing constantly throughout Precalculus, is I'd like to write Michael's position instead of at a particular time. I'd like to write Michael's position at time t. What do I mean by that? I mean, I'm going to write Michael's position as an expression in terms of t. And when I plug in t equals 0, I'll get Michael's initial position. When I plug in t equals 10, I'll get Michael's position after 10 seconds. So, Michael's position as a function of t. Well, Michael's y position is always 0. And Michael's x position is quite easy to describe. For every second Michael travels, his x position increases by 15. So I can simply write this as Michael's time position. Notice that if I plug in t equals 0, I get 0, 0. If I plug in t equals 10, I get that Michael's position is 150, 0, and I'm happy with this. So similarly, I can model Aaron's position, slightly trickier. Again, I have Aaron's y position is always 0, and Aaron's x position as a function of time. Well, Aaron's initial position is 10,000, and after every second, that x, this 10,000, will decrease by 8. So again, when I plug in t equals 0, I find Aaron's position is 10,000, 0. I'm happy about that. When I plug in, say, t equals 1, Aaron's position is 10,000 minus 8, which is exactly what I would like. So I now have Michael's position and Aaron's position. We describe these as parametric models for Michael and Aaron's position. In particular, this parametric comes from the word parameter. We're using t as a parameter to describe position. So in order to say when and where these people meet, all we need to do is ask, when is m of t equal to a of t? In particular, what t value will make this point be the same as this point? We can see that the y values are going to be equal throughout. So setting these equal, 15t equals 10,000 minus 8t, solving for t. So this is when they will meet. Where will they meet? Well, they'll meet at, if I actually compute this 10,000 over 23 and plug it into m of t and a of t, they should agree and give the same results. In particular, I can certainly say that the x position here will be this, and the y position will simply be 0. So this is a first introduction to parametric equations.